Hey there everyone, this is Jeremy McWhirter and this is my fifth lab, and here we're going to be working with magnetic braking, and that's associated with Faraday's law. So a little introduction getting into the lab. First we have to outline the goal of the lab. So in this lab we are measuring the effect that Faraday's law has on a bar magnet that we drop through a tube of aluminum foil, and that tube of aluminum foil produces the induced current while the bar magnet supplies the external magnetic field. Some of the fundamental laws that we're going to be using in this lab will be Newton's second and third laws, as well as Faraday's and Lenz's law, which those relate to the induced current produced in the tube of aluminum. And then we have Biot-Savart's law, which relates to the magnetic field produced by a charge with velocity. So then a preview of the results. So in the experiment, we found that it took the bar magnet to fall. It took 1.7 seconds for it to fall experimentally, and then in the simulated glow script code, it took about 3.08 seconds for the magnet to fall, and we'll get into the reasons why that differs later on in the lab. So these are the principal equations used. On the left, we have Faraday's law of induction right here. That's the induced EMF is equal to the negative number of loops times the rate of flux with change of time, and the minus sign is from Lenz's law. Which is because the induced magnetic field opposes the change in magnetic flux. That's why you have the negative. And then on the right, we have Biot-Savart's law, which is the charge and velocity crossed with r hat. And here you can just kind of see that it's the magnetic field generated with a charge, with a charge that has velocity. So that uses just an outline of the two equations we use. Next, here's the experimental data that we found. Hopefully, I guess the video isn't working, but it is a video of us dropping the magnet while in GPS. That's the tube of aluminum foil. So then here are just the initial measurements of the actual tube, and then the initial measurements of the magnet. And then we found that the average time was 1.7 seconds for it to fall.
40 centimeters.
All right.
It's down to, is it 90? I can't really see from here.
Yeah, it doesn't matter. It's when it comes out. Alright, ready?
I'm already recording.
Ready?
You guys have fun. Enjoy the rest of your day.
Okay.
There we go. All right, and next we have the glow script code. Here at the top, we're just identifying the constants with mu and mu naught and all that. And then later on down, we have the thing that calculates the change in flux that we use in Faraday's law down below here. And then here we have the part that includes Biot-Savart's law, which is defining the magnetic field. And then we're just defining the forces right here and then printing the actual amount of time it takes experimentally for the magnetic to fall. All right, and then this is the model created in GlowScript from the simulation. The simulated time was 3.079 seconds. And then just some things here, that the velocity in the tube is due to the force of gravity that is acting on the magnet. And then some reasons why this could fall slower than in real life is because of maybe the aluminum has non-ideal magnetic properties, and maybe this tube of aluminum had some different properties, and it wasn't an ideal tube of aluminum, as well as the magnet did rotate and bounce around in the tube, and the rotational dynamics just takes so many different magnitudes of math to figure that out. So that definitely has an effect on the falling time, whereas in the simulation that falls perfectly. So yeah, that's the model on the right. And then what if? There are two what if questions for this lab. So what if the resistivity of the conductor were reduced as close as possible to zero? How the dynamics of the falling magnet change? So if the resistance decreased of the conductor, then the induced current and the magnetic force would increase to compensate, because that would mean the change of flux would alter, and this would cause the magnet to fall even slower. Another what if is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into this, there would be no current generated within the ring or the tube, because the path would not be closed, and there wouldn't be current to flow. The best way to kind of relate this to is an open circuit. So the magnet, like there would be no induced current, and the magnet would just fall very quickly.